We're working with the same dataset that we used previously, the diabetes datasets from Scikit-Learn. We have 10 features for 442 diabetes patients. We have their age, their sexes, their body mass index, average blood pressure, and 6 serums. We want to see whether there is a relationship between these features and the target variable, so we can actually make a predictions for other patients, and we build a model based on that. So previously we used this data and we applied a linear regression model. We called it model, or a different name possibly, and then made a prediction on our test data sets. And the prediction score, the R-squared score was 33%, which is not a satisfactory score. So we need to work on this model to make it better. So now we want to improve the performance of the model and to make a better predictions. There is a concept in machine learning called feature engineering. It means identifying a set of or a subset of influential features that we have in our data that can best describe the relationship that exists or may exist between the features that we have and the target variable. So we want to see if we can find a better subset here because we have 10 features now. We want to see if we can actually find the most influential subset of features here. Or in future, if you're working in a data set that has even higher number of features, you might actually want to do that, to use feature engineering to identify the most influential features in your data and work on that, and based on that make a model that has higher accuracy. So let's now print out. We want to see what is the problem. Why do we have a low accuracy here? Do we have a common problems that usually exist when you develop a machine learning model? For example, underfeeding or overfeeding. Do we have those problems? So we want to figure this out. So let's print out the accuracy measure on the training dataset. So this is what I'm going to do. I'm going to make a prediction on the training data and put it here. So the model is called model, and I'm going to ask it to make a prediction on the training dataset. All right, and now I want to print it out. R squared on training dataset. And then I'm gonna ask for the R2 score, and I'm gonna give it the Y train and Y prediction, the actual value and the predicted value, Y predict train. So the R squared value on the training dataset is 55%, which is higher than what we had for the test set. I'm just going to do the same for the testing data set here, so we have both of them here. R2 score for my test data set and the prediction that we made for it. Right, so the R squared value for the training dataset is 55%, which is higher than the 33% for the testing dataset. So this shows that so it seems that the model is doing a little bit better, not a little bit, a sizable or a noticeable amount better than it does on the testing dataset. So we might actually have overfitting problem. So that's a hint. We can actually possibly work with the regularization and use regularization to improve the model. All right, so we want to apply the regularization on our regression model to see if we can improve the possible overfitting issue that it might have. So let's make our life easier and let's create a table to keep track of the R squared values for our reference. So I'm going to create a data frame and I'm going to call it the R squares. R squares. This is a Panda data frame. And then I'm gonna keep track of the algorithm that we've been. So right now we only have the linear regression model. So I'm going to call it LR for linear regression. And then I'm going to put these scores that we have, the R squares for the training dataset and test dataset, to keep them in this table. So R2 score for the training dataset, for the Y train and Y predict train, and also the RH2 score for the test dataset, so Y test and Y predict. All right. So if we print out actually this table, R squares, the table looks like this. So we have column linear regression and we have index 0, 1, and 1, 0 and 1 for the rows. But we know that this is probably for the training dataset and this is for test dataset, but let's actually rename these row indexes to make it easier for our future reference. Okay, so I'm gonna come here, rename our rows here. Okay, so I'm gonna R squares the name of our table and then use the rename command. So for index equal to 0, use train, and for index 1, use test. And I don't want to change the place of this, so in place must be true. So it would keep the place of these indexes. All right, so let's now print out the table that we created and we rename the indexes. All right, so this is much better than this one. You have the training and test labels here, so we know which one belong to which now. All right, now that we created this neat table to keep track of our algorithm performance, the accuracy score on the training and test, the R2 score, let's start applying a ridge regression model. So I'm going to first call the ridge regression. So from a Scikit-Learn linear model, import. The name of the ridge regression is just ridge. So I'm going to import it and then I'm going to create a copy of it as my model and name it whatever I want. I'm going to call it my ridge, and that's equal a copy of ridge model. And then in the parentheses you can specify the parameters for the model, for the ridge model, especially the penalty term alpha. So I'm going to specify alpha. I'm going to have alpha of, for example, 0.45. We can actually change this later to control the behavior of our model. So let's go with 0.45 now. And we can Let me go ahead and run this. All right, so next we can train our model to our training data set with the previous split that we already have. So I'm gonna go with that one, and I'm going to have the command for fit for the training, marriage fit, and then I'm going to give it the training data set. So that's going to be X train and Y train. All right, so our model is trained using our training data set. So that means that it figured out the slopes for our model. We could actually also do it here in the same line. So let's do that just to show you that this is possible to do. All right. So now our model is ready. We can make predictions. Let's make prediction on the test dataset. Y predict equal to our model names, my ridge, and then make predict on the X test. And then I'm going to print out the R2 score. So R2 score, Y test, the actual value, and my prediction, Y predict. That's about 35%. 35%, and here we had about 33%. So it actually improved it a little bit, about 2% improvement. We can actually play around with the values of alpha. So here, for example, let's actually change it. Let's for example decrease it to 35%. So I'm gonna rerun this. It actually, the accuracy on the RS score value decreased a little bit. So I'm going to increase it now, 55, for example. Not much. So I'm gonna go back with, for example, let's go back with the 75%. See how would that. So actually it's gonna go down right now. So I'm gonna go back to the 45. It seems that 45, there is actually, if you remember the 3 steps of machine learning development, one of them is optimization, the optimal or the best values or level for our parameters. So it seems that not every value works best here. So it seems that over 45 right now with the other numbers that we try has been better than the others. So I'm going to use this one. Now let's make predictions on the training data set. So I'm going to make Y predict train. Then I'm gonna call my model my reach and ask to make a prediction on the training data set. Right, so let's print out the R squared value for our new prediction, Y train, and our prediction, which is Y predict train. So that's 51 compared to what we had before, which was 55. So it looks like that the training, the accuracy, the RS score value for the test data set improved, and for the training data set, it actually a little bit decreased. In general, it means that the gap between the accuracy measure for the training and test data set got lower and lower. All right, so let's now add to keep track of our RS score value. Let's actually add the RS scores for the ridge model to the table that we had. So I'm going to call the RS squares and add the ridge model, ridge, and then I'm going to give it the R square values here that I had. So R2 square for the training first, and then for the test data sets. Okay. So let's print out the R square table now. Right, so as you see here now, we have the linear regression model and the ridge regression, the regular regression. For the training dataset, the R square value is 55% for linear regression and 51%, 52% for ridge regression. So it's a little bit actually decreased. For the test dataset, it was 33%. Now it's 36% almost. So the gap, as you see here, before it was about 22%. Right now it's less than that. It's less than 22%. 15, about 15, about 16, probably 16%. So, and we can actually play around with the values alpha to see maybe we can actually even improve the gap or lower the gap even more. So now that we have developed and the regular regression, the ridge regression model, and we have the scores for this. Let's move on to the next regular regression model, which is the lasso regression. So let's develop the lasso regression for our problem. So from a Scikit-Learn, let's import model, the Scikit-Learn linear model, import. The name of it is lasso, so it's L is capital, and then we're going to make a copy of this. So, and initialize the values for parameters. I'm going to call it my lasso, and that's equal to lasso. In parentheses, we can specify the parameters, especially the penalty term alpha. So I'm going to go with alpha equal to, for example, the same that we use for the ridge, 45%. All right, now we can actually train our data, train our algorithm using in the same line. So let's do that. Fit here, and I'm going to give it the training data, so X and Y here. All right. So later we can actually see, we play around with the values of alpha to see if it changed the performance of the model. So let's now make a prediction on the testing data set. So I'm going to call the yPredict to keep our prediction, my lasso. I'm going to call my model to make a prediction on the test data set, xtest, and I'm going to have the R2 score for our prediction, the real value y-test, and our prediction yPredict. So it's about 33%. Let's try it with different values. So I'm going to go with 35%, lower, 33%, let's go lower, 25%. Oh, it improved a little bit. Let's go with 15%. So it's almost the same. It's about 34. Let's go lower. How about 5%? But it decreased, so I'm gonna go back to 15%. All right, so let's also make a prediction. You can also, by on your own, you can play around with this value, alpha, the parameters, to change the behavior, maybe find the optimized value for this. So for now, let's go and make a prediction for training data set. So I'm gonna call it y predict train, and then I'm gonna call my model to make a prediction. Predict on the training data set x string, and let's print out the R square value, R2 score for y train and y predict train. So it's about 54%. All right, so let's add the R2 score for lasso to the table. So it was called, what it was called? It was called the RS squares. So I'm gonna call RS squares, and then I'm gonna call it lasso. Then I'm gonna give it these two values: the R2 score for training first, and for the test as well. All right, so now let's print out the RS square table. Squares, RS squares. So here we have the table.